Hole cutting 101. What is this? Those are nails, of course, but I thought we were going to learn how to cut holes in this class. Ah, yes, we are. You still remember how to use a hammer and nails from high school, right? Yeah. It's been a couple of years, but I still get the gist of it. Great, because we'll need a hammer and nails in order to define what a hole is. Ladies and gentlemen, the fundamental theorem of calculus. Alright, class, let's define what we mean by a hole in this course. Definition. A hole is an opening through wood which has boundary given by the limit as n goes to infinity of n equally spaced points on a circle. So, you see, we will have to use a hammer and nails to be able to create holes by visualizing a circle and making nail holes all around its boundary. But my friend said that a hole is just an opening through wood made by a hole cutter. Ah, you are getting ahead of yourself. We don't know that that is true yet. Okay. Will hammer and nails be on the midterm? No, but it will be on your homework. Alright. I guess I have to pay attention. What a drag. Does this sound familiar? Aren't integrals just antiderivatives or something like that? But why do we have to define them as limits of sums? If there's a clean, easy way to compute integrals, why would anyone ever bother with computing finite sums and then taking their limit? In this analogy, the holes are like integrals. The hammer and nails method of creating a hole is like the finite summation way of evaluating an integral. And we will find that the fundamental theorem of calculus is like a hole saw. Alright, class, today we have a theorem to cover. Pay attention, this is the most important theorem of the course. You can tell because it has fundamental in its name. You see, when something is labeled fundamental... Yes, we know. Oh, right. Yeah. Anyway, here's the theorem. The fundamental theorem of hole cutting. A hole is an opening through wood created by a hole cutter. Finally. You see, class, this theorem is instrumental in this course because it will allow us to make many holes easily and with very little physical effort. In fact, it allows us to use a completely different tool to perform the same job. It allows us to avoid taking a limit of finite approximations and to instead just directly make the entire hole all at once. Some people find it counterintuitive that such a method of hole creating exists, but there's a proof of this theorem in the book, so in fact, it's logical. Yes, just like the fundamental theorem of hole cutting, our fundamental theorem of calculus provides a somewhat counterintuitive way of computing integrals. It allows us to compute many integrals easily, with very little effort. In fact, it's a completely different tool for computing integrals. It allows us to avoid taking a limit of finite approximations, and to instead just directly evaluate the integral. Let's see this. Here is what the theorem says, a fundamental theorem of calculus. Let f of x be continuous on the closed interval from a to b, and let capital F of x be an antiderivative of f of x. Then, the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. Here's a quick example to illustrate the difference between using a hammer and nails versus a hole cutter. Using finite sums versus using the fundamental theorem of calculus. Example. Compute the integral from 3 to 10 of x squared dx. Let's take a limit of finite sums. Hold on to your seat, this will take a hot minute. To help this go by faster, I will state what rules I'm using to cross over an equal sign, rather than state what the terms are by name. Here we go. To start, we need to figure out where our right endpoints are if we divide the closed interval from 3 to 10 into n equally sized subintervals. Well, since those lengths are all 7 over n, we find that the right endpoints are 3 plus 7 over n times I, for I equals 1 up to n. And so, we are ready to begin. Since 7 over n is a constant, we can factor it out of the summation. Also, we FOIL the 3 plus 7 over n times I squared. Since 7 is a constant, we factor it out of the limit. Also, we split our summation into 3 separate sums. Next, we factor our constants out of our 3 sums. Using summation formulas, we condense our 3 sums to the following. We simplify in 3 locations, and we distribute the leftmost 1 over n to the right. Now, we break the limit into 3 limits, and factor out the constants. Finally, we use limit rules to compute the limits, and simplify however we can until we obtain a concise answer. We get 973 over 3. Alright, so that took a while. Let's see what happens when we use the fundamental theorem of calculus. Notice that 1 over 3x cubed is an antiderivative of x squared, since the derivative of 1 over 3x cubed is equal to 3 over 3x squared, that is, x squared. In fact, the method of increasing the power of x by 1 and then dividing by that new power works whenever our new power is non-zero. Okay, here we go. The integral from 3 to 10 of x squared dx is equal to 1 over 3x cubed evaluated from 3 to 10. That is equal to 1 over 3 10 cubed minus 1 over 3 3 cubed, which equals 1000 minus 27 over 3. Hence, 973 over 3, just like before. Wow. Here, the power of the fundamental theorem of calculus shines bright as day. We were able to compute the integral with 100% accuracy in only a few short steps. Compared to the method of limiting finite approximations, this was a breeze. And so, the fundamental theorem of calculus is the hole cutter tool, in a world where holes used to be cut by hammering nail holes around the border of a circle. And that's it for today. Math, just like anything else in life, gets easier the more you see it. Take for example your favorite movie. I bet you could watch it for the 973rd time and still find some new Easter egg in it. So now that you've seen this video n times, see if you can fill in any gaps by watching it n+1 times. And if you have any questions, be sure to leave a comment down below. If you found this video helpful or interesting, be sure to give it a like, as it helps support this channel. New videos are posted every Tuesday at 2. To never miss out, be sure to subscribe and hit the notification bell. Thank you so much for checking out this week's video. See you Tuesday!